Hello, so it's pleasure, pleasure to introduce our next speaker is Professor Stephen LaValle. He's a professor of computer science and engineering at the University of Oulu, and with particular focus on robotics and VR. I would ask Professor LaValle to join in and share his screen, if he can. Yes. So over the years, he's held several positions at the university, some from University of Illinois, at Stanford, and at Iowa. In research, he became most known for his contribution to the RRT algorithm and his book, of course, Planning Algorithms. And another aspect that makes his experience quite interesting is his openness to collaborating with industry. So he was an early founder and chief scientist at Oculus, and was VP and Chief Scientist for XR at Huawei Technologies as well. We thank him for joining us all the way from Finland. Please welcome Professor Stephen LaValle.
Okay, thank you very much. Hopefully you can hear me okay?
Yes, we can. Yes, we can.
Okay, very good, thank you. First of all, I just want to apologize for not making the trip to come there. So I usually get annoyed if I'm in the audience and there's an online talk. So here I am doing it, so sorry for that. I moved to Finland in 2018 and built up a group called the Perception Engineering Lab, which has a couple of dozen people and is co-directed with myself and Professor Timo Ojala. And there's also actually 5 members from our group are there in the audience right now. Maybe you guys can raise your hands. There's Bashak, Marku, Juho, Kshitij, and Catherine. So hopefully they're jumping up and down. I see the room's kind of large there, so hopefully you can see them. I highly encourage you to talk with them. So what do I want to talk about today? Well, one of the experiences I got developing the Oculus Rift was wondering about how to assess quality. Are we making a good device? Hard to tell. After living in Finland for a few years, the culture here is very communications oriented, largely influenced by Nokia. And we tend to think of things like quality of service. And then in between, so if you get down to the next level here, QoE, quality of experience, we've all seen that coming up in a number of different contexts, and that starts to involve humans in the process. Social psychology, cognitive psychology, vision science, things like that come into play. And I've really wondered about the quality of XR, VR, XR, AR, MR, whatever you want to call it. And so what exactly is going on there? What exactly is needed? And it's tricky because it involves a low-level integration between the humans and these engineered systems that we're putting together. And the criteria are somehow closely interleaved. Many factors contribute to making a good, let's say, VR or XR headset. And again, I had I could go on sort of go off on a tangent and tell some interesting stories, but I had a lot of experience, especially at Oculus, but also at Huawei, in trying to determine what's working and what's not so well. So there's many factors that all come together. You improve one and then others become more important, and it's just an endless kind of cat and mouse game, it seems, to try to figure out how to improve things. If you don't get it right, you end up with the experience being not so believable, or fatigue, and then sickness in the worst case. And of course, there's adaptation across people and variation across people. So very difficult. And then if you're not really sure what the use case is going to be, which seems to be like this a lot in the industry, then it becomes even more challenging because it depends on that. How do you observe a system? Well, as roboticists, we certainly like sensors and we like making observations. So what happens in a VR XR kind of system? You can measure the device itself. You can measure the optical system, the audio capture. There's sensors themselves, cameras and inertial measurement units. There's even full robotic systems made by Opto Fidelity, where you can stick a headset on a virtual head and it starts moving around, and it has a camera that replaces the eyeball, where the human eyeball would be, so that you can take measurements. But don't forget that the humans are also an important part of the system. So what can you do with them? Well, mostly you're limited to just asking them a bunch of questions, which is okay, gives good information. You can hook biosensors onto them, and that becomes a little more invasive or complicated, let's say, at least. But that can be done as well. What I'm really curious about, though, especially coming from robotics, is what theoretical models can these measurements that we take be compared to? How do we know that we're getting close to some kinds of ideals? What I think is happening is there's an emerging discipline that I call perception engineering. And I consider myself an engineer, mostly a roboticist, but also into VR and a number of other things. But if you look back at the history, think about the sciences that expanded or adapted or got applied, let's say, to create fields of engineering. So physics, our understanding of the world around us and being able to mathematize the world around us, write equations, be able to make predictions, do experiments that confirm these things, was very important. And then from that, you get civil engineering, building better bridges and buildings and so forth, roads, mechanical, electrical engineering, chemistry and biology working in the same way. So I see the same kind of thing happening with the application of the science of perception and neuroscience. So the things we understand, and together human physiology as well, these things we understand from these sciences, I believe, are ripe to apply to this field that I'm calling perception engineering. Now, in civil engineering, the goal is to build something, let's say, like a bridge or an aqueduct. What are you building in perception engineering? What you're building or creating or designing or analyzing is a perceptual illusion. So you're creating an illusion. That illusion lives in the organism, human or otherwise, that you've designed it for and targeted. So we want to make some kind of mathematical models of this and try to understand this so we can do our engineering kinds of things, like do design, analysis, prediction, prove theorems about it, even whatever things we might like to do. I'm very grateful that we have a European Research Council advanced grant that's supporting most of my group. It's very unrestricted funding, and it lasts for 5 years. We're in the second year now. And the idea is to develop unified mathematical models that span both engineered systems and organisms. So not only covering VR or XR, what you might think of for a human, or rodents or fruit flies, whatever you like, but also covers systems that we can construct completely from scratch. So I can target a robot with virtual reality. So why am I interested in that? I want to introduce a kind of theoretical foundation or mathematical foundation that lifts VR to a more established engineering discipline. I'm kind of frustrated after decades of I would say being in robotics and also seeing this in VR. I think that people outside of both of those fields tend not to take us so seriously as a scientific discipline. They view it more as like a technology and business and maybe an application field that's ripe for some other theory or some other kinds of techniques. And I think that's not really the case. I think both robotics and VR, XR are both individually have very deep questions, are very unique kinds of fields, and there's scientific aspects to it that are as fundamental as you want to get, really. And I'd like to bring that out through mathematical modeling that shows the uniqueness of it. So it'd be very analogous to the way the theory of computation works for computer science, or the parameterized differential equation formulation that you get for control theory, x dot equals f of xu. So something similar to that. So I think we would gain deeper insights into perception engineering if we can try to unify the problems across many fields, much like control theory does or theory of computation does. And then we can try to better explain and predict VR phenomena through specializations. And I think there are direct benefits for robotics as well. So our general long-term plan, G is general and S is specific. We want to have this kind of general theory of VR. And again, you can call it XR. The names keep changing for political reasons and things, but and then there's a division across the VR for organisms and VR for robots. So when I say VR for robots, I mean the robot is having the virtual reality experience. And then there are many specific cases, and we'd like the specific cases to be unified under some general umbrellas, and then the whole thing to kind of fit in some general way. Now, the most general form might not cover every special case. It may not encompass everything. Physics works very similarly like that. Okay, there's some laws that cover sort of large swaths of what you want to achieve, but not sort of everything, and that's perfectly fine. And then at the foundation level, we have experimentation, both from existing literature and new experiments that we do in our lab and that others will be doing. And then there's also a lot of benefit from simulation. So what does VR for robots mean? Well, we have this very famous actor here, Markku Suomalainen, who's in the audience there. He's actually serving as a VR display for a robot that's experiencing virtual reality. We just took a simple vacuum cleaning robot, and Markku was presenting obstacles to the robot to fool it into thinking that it cleaned the entire room, which was actually which the robot thought was a small room, but we, becoming some kind of gods that fool the robot, know that it's much larger. So we mathematized some of this in a paper for IROS 2 years ago, and that gives you some idea of what it looks like on the robotics side. So what does it mean to create a perceptual illusion? Well, one of my favorites is the Ames room illusion. So you can see two people there. They are actually roughly the same size, but this guy looks much, much larger. And that's because when you look at the top-down view, there's a kind of depth cue trick going on where the user looks through a viewing peephole. One of the reasons why is that they do not want stereo vision, because if you could see with both eyes, then you would not have this illusion. This entire room is distorted and stretched so that the woman was actually standing very far away. Even the tiles on the floor were distorted in some way so that they would look perfectly straight when you look at it through the viewing peephole. So you're able to move an object back and forth along this axis here without the human being able to really detect it, that that's happened. So how does that work? Well, if you look at just a basic projection array model, pinhole camera model, then you can place an object back and forth along the projection ray, and that would show up in the same place on the image plane. So I'm going to call that a pre-image. And then more generally, you can make a theory of pre-images that says, we have any kind of physical state space. It can be a configuration space, like the kinds you might use for motion planning and robotics. It can have velocities, other stuff in it. But generally speaking, obstacles, things like that can be included in this general space. And then what we want to talk about is a sensor that we might have. We may have more sensors than one, but let's just say there's one here. Then it's a mapping from states to observations. So in this particular model, we can have other models, but today, let's just say it goes from states to observations. Then the thing I'm interested in is what's called the pre-image. It's the set of all states that produce the same observation. And you think about it, that's a lot of uncertainties being somehow taken into account or handled by such a sensor. The sensor is not measuring everything about the world around it. So for example, if you have a distance sensor that just measures the distance to the wall in one direction in a mobile robotics application, there's a lot of places where you could move that sensor around and it would still measure, say, 2 meters. You could be all over the place in some complicated room and still get the reading 2 meters, different rotations and positions. So the pre-image could be quite large. So you can think of a sensor as being kind of like a bread slicer for the state space. You put a state space in, you define a sensor, and then it chops up the world, the state space into these slices. Inside of each slice, you get the same observation. That actually naturally induces a partition of the state space. And then you can build sensor fusion methods as follows. So think about triangulation, not the process of making triangles, but something more like sensor fusion. So all that is if I get multiple readings from either different sensors or perhaps multiple readings from the same sensor if there's time involved, but let's just say it's multiple sensors for this example, then you just simply intersect their pre-images to figure out what the possible states are. And you can make a Bayesian version as well, that's fine. So stereo vision works by just intersecting single ray pre-images. So we have one camera, we have all this ambiguity about where an object might be. Just like you had to look through the special pinhole for the Ames room illusion. This kills that because you have two different eyes or cameras here in this case, and then you know exactly where the object is by intersection of pre-images. There's the ancient triangulation that I showed a picture of, which basically is just keeping the angle between two landmarks fixed. Then you end up being on circular arcs for pre-images. Another case that's very simple, which I'll elaborate on a bit, is trilateration. So you have 3 towers out in a 2-dimensional field, let's say, and then you're the pink object here with a sensor. And if you have a sensor if you have, let's say, 3 sensors, we can say technically, each one gives the distance to tower 1, 2, and 3 respectively, then the intersection will tell you exactly where you're at, right? So if you only had 2 of them, then there would be 2 different points that you could be at. But once you have the 3rd one, you can figure out where you're at. So now let's think about fooling such an engineered device. Let's suppose a robot or maybe a human with a kind of GPS unit is running around in a field. You could take you could, as some sort of evil gods, you could change the signal intensity on, say, tower number 2, assuming that this distance measuring sensor is using signal intensity as a way to guess what the distance is. Let's suppose that it's been calibrated for that. Maybe the people using it have no idea how it works, but the engineers or the gods here who are trying to do VR and fool people and robots with it know this. So if you do that, then if you get it just right, if you get the intensity just right, instead of being in the pink place, you'll think you're in the yellow place here. So if you think about it very generally, if I just have 1 tower and I don't have 3, so I just have a single sensor, I can change the intensity and fool you into thinking that you're just about anywhere in terms of distance away from the tower by just changing the intensity of the tower and assuming your device is calibrated as such. If I have two towers, then there's only an interval of possible distances that I can make you believe you are away from one of the towers. If you have three towers, then you have to get it exactly right. That was this case here that I just gave. If you have three towers, then you can only move from the pink disk to the yellow disk, and that's it. So it's interesting in that sometimes your ability to create an illusion is very fragile. Like you just have one kind of point of opportunity, and you'd better get it exactly right. And if you don't get it right, then the intersection, this triangulation, becomes empty, and it becomes an implausible case. It's analogous to cognitive dissonance in organisms, so something that psychologists know about. So I think that's really interesting in that in some settings you have robust illusions. You can create illusions and have a lot of slop in the parameters. And I think you see these kinds of things happening with VR headsets all the time, by the way. So there's some illusions and some things you're doing, you have a lot of freedom to kind of slop around. And sometimes you'd better get it exactly right, or there's fatigue and nausea and other things going on. So we're not only just want to deal with a single measurement, but we have agents that interact with the world. Again, by agent, I use it as a general way to describe either a human organism or a robot. So let's say it's either one of those. And it can interact with its environment. It chooses actions, right? And you want to be able to trick it in spite of its ability to go out and interact. So we're going from perception to interaction. That's the challenge. Well, the mathematical model for that is this kind of scenario here. You have an external state space, and you have an internal kind of information space that corresponds to the brain of the robot or the organism. And then you have a sensor mapping H, like I've given already, and then you have this kind of control mapping here, or strategy or plan map, which takes the internal information state of the organism and chooses some action that gets applied. So it becomes actuation or some change of energy or accelerations or something like that out in the external world. What you notice about this is it's a beautiful kind of symmetry. It's a kind of dynamical game, dynamical game, I guess, or a kind of a multi-dimensional control system kind of problem here. But it's important that there's two different sides to it. There's the external side and the internal side. And then if you want to do VR, assuming you're some kind of clever gods, then you just replace this external part here. There's still an external state space, but you just put some devices that the agent that's being fooled is not aware of. There's a kind of stimulator, which has a display in it, for example, in a normal VR terminology. There's an actuator, which might be a controller in normal VR terminology. And then there's a virtual world generator, VWG, that acts as a kind of simulator that provides all the things that are needed so that it can maintain a kind of consistent worldview for the agent that's being fooled. And pay attention that the people doing the fooling are like gods compared to the agent. They have access to more information. They may know about more state variables that the agent doesn't know about. This is very close to what's going on in cognitive neuroscience, things like Friston's free energy principle, predictive coding, Bayesian brain hypothesis. I don't have time for this, but I just pulled one of the figures out of their field. We have a couple of perceptual psychologists and cognitive neuroscientists in our group as well. So we're very I hate to use the overused word interdisciplinary, but we have people from different disciplines and we work very closely together. One important part of the modeling is information spaces. I've been interested in this going all the way back to my graduate school work. And this notion of information comes from von Neumann and Morgenstern in the context of dynamic game theory. I said there was a kind of interacting game, a dynamical game that was going on. This is not like information theory, so it's not Claude Shannon's notion, which came a little later, actually. It's not about bits, but it's more about hidden information. So if you know about POM-DPs from a lot of AI research, it's showing up in robotics a lot, then this would be related to that. It's closer to that, but not necessarily probabilistic. So it has to do with observability. What can you observe? You generally observe history information states, which is all of the actions and observations that have been given so far. And the space of all possibilities of that is enormous. And you want to try to reduce or collapse that down into something smaller. I'm trying to figure out what needs to go into the agent's brain if you're designing it. This is more fundamentals of robotics, I would say. So if you want to solve some tasks, you want to figure out what kind of brain does the robot need? How small can it get and still be able to, let's say, robustly solve tasks? And so moving along from left to right, the history keeps growing in some way, but we want to collapse it down to something smaller. And we have some recent works on that, on this, which you can see from Frontiers in Neurorobotics and also Wafer Vadim Weinstein, Bashak is there in the audience, so you can talk to her about that as well, and some other guy who's giving the talk now. We have a lot of different examples of that. One of the most celebrated ones is the Kalman filter at the bottom there. So these kind of collapsing of information spaces comes all the way down to mean and covariance being enough to fully parameterize the information space. That happens for linear Gaussian systems and so forth. Even the probabilistic version is a Bayesian, just Bayesian filtering, and that works under a number of settings and assumptions. But there's much more that can be done here, and we have this kind of general theory that says that there's a minimal one that always exists and is unique. And I think that's quite a powerful statement. It gets at the limits of what you can do with planning and learning. And then there's a whole space of partitions called partition lattice, and that gives you, in some sense, a notion of the resolution over which this state space has to be not exactly represented, but it's implicitly encoded by these information states that you have. And I don't have time to go over that, but I just wanted to give let's just show a picture of it, and that's it. Not even a picture, but just give you the idea. If you want to do virtual reality in terms of these information spaces, you could have a passive approach that just tries to make sure that you do stimulation and actuation in the physical state space, and it could be somewhat passive in the sense that you don't want the internal information space trajectory to be altered. Or you can make it more active. There is a different kind of information space trajectory that's obtained for the agent, but hopefully it's one that's plausible, and that's something that becomes very important, just as I talked about in these very simple examples of the intersections of pre-images. Turns out there's more kind of generalizations of these intersections of pre-images that become relevant. And so I think this becomes a very nice way to look at things. And then one thing to note is that it's easier to fool an agent that has a smaller information space. So if the kind of the brain of the robot is very tiny, just like you might have an easier time fooling an ant, although people have been famously kind of surprised at how smart they are, but still I think it's a little easier to fool an ant than it is a human. At least a roundworm or something is easier to fool than a human, hopefully. So we have these kinds of things going on as well. So you may want to, if you wanted to make a robot that's robust, it's really hard to fool it with virtual reality, then you may want to give it a bigger brain. And then this mathematical formulation may help you to figure out exactly what needs to be done. You could also talk about error metrics and continuous information spaces, and maybe talk about an integral of error over time. And that feels very close to models of things like forced fusion and adaptation and fatigue that show up in nausea even as well, that show up in virtual reality research. I'm just about finished up for the most part. One of the most important things is black box versus white box. So if it's a robotic system, we may know everything about it because we built it ourselves, let's say. So we have the opportunity to understand virtual reality at every single level. And it can be 100% pure virtual reality in that every single sensor can be fooled. That's pretty hard to do for the human. It's always partial in some way. And then because you don't have the brain in a vat kind of scenario going on. And then the robot could be a black box, though, if you steal somebody else's robot and you want to do virtual reality on it to figure out how it works. For the organism, it's closer to a black box, but maybe a gray box that's getting wider all the time as we understand more and more about organisms' work from psychology and neuroscience and even anatomy, physiology kind of work. We spend a lot of time in our group on sort of the more practical end with telepresence involving a mobile robot, 360 cameras, and a VR headset. So it's a kind of tele-embodiment. I'll just kind of give you a brief taste of that. So one of the things I noticed working at Oculus, when we move a virtual character in VR, it was a lot more comfortable for people to just instantaneously start moving rather than gradually ramping up. We first thought gradually ramping up would be more comfortable. So what acceleration profiles are more comfortable? It's quite a counterintuitive thing in VR, and this would imply the same thing for this telepresence case. So we'd like to understand that. So what are the general perception-based criteria that would make people more comfortable in this kind of telepresence scenario? And what kind of filtering can we do? So if a robot's moving around with a panoramic camera, one of the most obvious things to do is to unwind the rotations of the robot. So you can just, because you're looking in all directions simultaneously with the camera, you can undo the rotations of the robot. This is more comfortable as the robot moves around. How to do planning, how to do motion planning and control, or how to share control with the user as well becomes very important. So just to summarize, this is our kind of long-term plan, which I mentioned, to develop these kind of general unifying theories of virtual reality that extend from organisms to robots. Remember this big model of the rising field of perception engineering. And I think I've made all of these points already here. So why do we want to do this? This will help guide us on where to look, how to predict outcomes, provide explanations, analysis, do the engineering kinds of things in this field. And finally, I want to point out that we have a couple of papers at IROS. So one of them, the first one is about shared control exactly for this mobile robot telepresence scenario. And I see 3 of the authors are there in the audience you can talk with. And then we have another paper that does have pre-images involved in mobile robots, but it's about touch sensors. And the first 2 authors are also there in the audience. So you can look at their papers later in the conference. Thank you.
Thank you for that talk, Professor LaValle. This actually captures sort of the essence of the workshop, also how VR and robotics can feed each other. I open the floor to some questions from the audience here or online. Okay, so there is a question online. Professor LaValle, can you read that?
I don't know if I can. Let's see. I'm looking to
in the chat, maybe. How far are we from developing the perfect XR headset?
Oh yeah,
ideal XR headset.
Yeah, that's great. So that's really great. So I think in a robotic setting, it won't be a headset, but in the robotic setting, we can make ideal XR, and I think that's impressive. And just to know that we can do that. For the humans, I think there's no such thing because again, it cannot be 100% virtual. You cannot fool human proprioception. The ideal, well, ideal in a scary way or evil kind of way, maybe something like the brain in a vat, and I don't know what that looks like exactly, but so I will say there will always be some kind of flaws, and most of this is kind of running around creating illusions that are kind of in the shadows and these kind of pre-images that hopefully make people have some good experience and are not experiencing some adverse side effects. But I think there's, I would say it may not even be a reasonable question to ask. I mean, it's a fine question to ask. I'm not insulting the question after, but I'm just saying that it may be kind of just on basic principles unachievable.
Okay, time for some short comment question. Anybody else? I was just curious if you could comment on. We always talk about this uncanny valley for humans going from reality into virtual reality and back. So I think this kind of formalization might also help understand that. Would that be something?
I think it could very much. If we go, that's an interesting. I haven't thought about that, but it's a good idea. If you go to like this error metrics kind of formulation that I gave here. So if you could then maybe quantify how close you're getting to reality, whatever that is, and then start to measure the proximity to that. And I could imagine then, yeah, some kind of study where there's a, when you're really far away, everybody's happy. When you're close, then it becomes uncomfortable in some way. And then when you hit it exactly right, then you're fine again, right? And I think that's a really interesting idea to sort of quantify and analyze the uncanny valley, at least in some contexts, for that. I'm a big fan of staying away from the uncanny valley. I think it's important to use our creativity in the creation of VR content to stay far away from that. But and we've all seen robot motion planning kinds of applications to digital human generation and stuff. And many times they end up looking kind of stiff and not moving so right, and it's difficult to get those things. And then animators create such beautiful kinds of motions and things, and so it's challenging. But that's where I would try to stay more on the creative side and not try to get too close. But these kind of metrics would, I think, help in that direction to analyze these things.
Okay. Yes. Thank you. I think we can close this talk here. Thank you very much again, Professor LaValle.
Thank you very much for the invitation. Sorry again that I couldn't be there in person. Please chat with my group mates. I'd be happy to meet with you. Take care.